So we are HE Solar. I'm Shelby. I have Cameron and Steven here with me today. I'll go ahead and show them in the camera since we're doing recordings as well. Okay.
Cameron.
So I'm going to go ahead and start off, and then I'm going to pass it off to Steven and Cameron, but I'll go ahead and give you guys the intro. So a little bit about us so you know what's going on. With a desired need for sustainable energy, solar panels have become the most efficient and environmentally friendly source of energy that has been provided to us. Our technical mentor and lead sponsor, Mark Summers, created the foundation of this project and has created the dual access tracking system for us that we are working on today. Our co-sponsor, HE Solar, has provided us a Panasonic solar panel that we are using on this project, and that is how we are. This picture right here in that center, that is the solar panel in its current state, so you can kind of see it. The next slide kind of shows you what is on that solar panel, so you can see that Panasonic solar panel in the structure. Then you have the linear actuator that is tilting it, elevating it up and down. You have a gear motor system that will give it that azimuth rotation. And then we have the lockable turntables, which will allow it to rotate. So just a little bit so you know what we're talking about later on. So in our problem definition, the overall goal of this project is to get the solar panel to orient itself to face the sun at any point in the given day using a GPS tracking system. With that major goal in mind, we have two problems that focus on the improvement of mobility of the solar panel overall. So this is something our customer has presented to us the first day of our intro, and that is to stabilize the azimuth and the elevation of the solar panel. So in that right picture that you all see, it kind of lets you know, like, so if the sun's right there where it is, elevation angle would give you that tilt, that elevation. And then the azimuth would be rotating so that you would face, north, south, west. And then I put that picture right there again so that you can see lockable turntables, gear motor, and linear actuator. Those are going to be important later in the PowerPoint. So I'm going to go ahead and pass it off on my teammates. They're going to go ahead and present the azimuth designs.
All right, so with the lockable turntable, the current state is the bottom plate will be fixed. At the moment, it's fixed to like a wood panel. They'll eventually be switched out to be cement in Mr. Summers' yard. We quickly found when we got down there, we're taking it apart and messing with it. Can we play this? Oh, yeah.
Yes.
You'll see here in this video, it quickly becomes unscrewed. So this is us tightening it, and with the bottom plate fixed, it just comes undone. So we came to the conclusion that the problem was it was actually fixed to the wrong plate. So currently it's the pulley is screwed into the bottom plate, and it's unscrewing itself when the belt turns it. As you see in this right picture, the belt is turning it and it becomes unscrewed. So our objective is to now find a way to fix that to the top plate without having to completely reorder a new turntable. And I'll pass that to Steven.
So we came up with two designs. The first one is the insert design. And basically what this would do, there's a hole in the turntable. It would fit perfectly into the hole. And the pulley connector would sit right on top of the insert. And with this design, it would be very easy to operate and like take apart. And that's one big thing that Summers wanted us to consider in our designs. And then for the second design, we call it the stabilizing frame. And for this design, we actually 3D printed it, and it's right here. But this design is the better design, to be frank, because what this one does is it allows the pulley to comfortably sit on this plate, and then there's a pin that allows it to not rotate. It constrains the pulley. And this is our concept selection matrix.
So for the concept selection, we did come to the conclusion that the stabilizing frame here was the better choice. The real problem with this stabilizing frame is, right when we showed Mr. Summers, his first question was, that looks great, how do you machine that? And when we went to the makerspace, Dr. Talley was walking around, he checked it out, he's like, oh, that looks really cool. How do you plan to actually machine that? So that's our problem at the moment. Machining is going to be an issue, so we're trying to find a way to combine the two ideas, the stabilizing frame and the insert, to make it more machinable and something we could actually make. And then pass this back to Shelby.
So they got done talking about the azimuth. Today I'll be talking to you about the elevation. So this is my conceptualization, stabilization of the tilt. In the far left down bottom picture, you can see that we kind of got the numbers as to how far it actually tilts or how far it will be tilting with the actuator's mobility to give it to do that or to allow it to do so. Just some need to knows that I found the numbers. The solar panel weighs 40 pounds, roughly 41 pounds. The maximum wind load of the solar panel that it can take is 130 miles per hour. It has a max rotation of 90 degrees, the whole solar panel itself on the axis of that circle. It can rotate from one point, if that one point it's sitting straight up, to the point of its maximum tilt, that it rotates 90 degrees on that circle. The actuator need to know is the load capacity for that actuator that is on the far right side of the solar panel. It can lift a max capacity of 169 pounds. The rate at which it pulls power is at 3.5 amps. That's its max amount of amps it draws in. It doesn't necessarily need to have that full 3.5 amps, but it does require 12 volts DC direct current. The diameter of the holes in the actuator, the ones that are connected to the threaded rods currently in that bottom left picture, that's what's holding it right now. That diameter is at 1/4 of an inch. And the length of the full extension of the actuator that it pushes is about 8 inches. So that can kind of give you an idea of like what the current state of it is, the math that I kind of put into play, along with other research I had, like looking at other solar panels that are on a dual axis system, like how are they centered, how are they able to go up and down. And then, so I'll go on the next slide. So the design ideas that I had for stabilizing the elevation of the solar panel was to, 1, center the actuator in the middle, or 2, add another actuator on the opposite side from the current actuator. That second idea is something that we kind of all had, but we all kind of turned away from early on because I'll get into that right here. This is the current. Let me just show you a video real quick of the current, like how it's currently elevating, so you can kind of get a general idea of what it looks like. And then in my head, or in our heads, hypothetically, this solar panel is only going to tilt 15 degrees every hour. So when I was turning the solar panel on, turning it off, that's about how far 15 degrees would be in it moving in its rotation throughout the day. So I kind of wanted to give a gist of like every hour that's going to be the shaking it might have when it's actually being used in real life. So I'll go through that first design idea, adding a second actuator on the opposite side. In this SolidWorks model, I put 2 actuators on either side, and you can see both of them working and being used. This would provide this would stabilize the solar panel. However, this might require major precision in connecting the 2 actuators and getting both of them to work automatically at the same time. It might cause damage to the overall structure. And then I also thought that it might not be ideally necessary to add a second actuator because both actuators can produce a load capacity of 750 newtons or 170 pounds on average when the solar panel itself is only 40 pounds. So I thought, with the actuator we have as is, we shouldn't really necessarily need to purchase another actuator in that process. So next idea would be centering the actuator. In this top right photo, I put the actuator in the middle, and I came up with the idea that we should take those two threaded rods and take them all the way across. The length of those threaded rods would only need to be 4 feet, and then we would need 2 of those. We can purchase those steel threaded rods, 2 of them at a 1/4 diameter at 48 inches length long. That will give you the 4 feet that you need. The next video, I put a motion of like how that solar panel would move on SolidWorks. And then this is my concept selection matrix. We were thinking centering the actuator would give better means to cost. It would stabilize it like it would adding a second actuator. However, the ease of operation would be easier centering the actuator, given that adding a second actuator would rise complications in having them be synchronized and pushing that solar panel up at the same time. It could cause damage. And then the customer preferred, or is leaning more towards centering the actuator rather than risking damage to the solar panel by adding a second actuator. And that's our overall presentation.